Let's continue with part B of this week's lecture and keep learning about coordinate systems. And maybe you're asking yourself, why can't we just use a flat map? Well, the Earth is curved, but maps are flat. So you're going from a 3D to a 2D. So to create a map, we have to represent a curved surface on a flat surface. And so if you were in class with me, like in a physical class, like I normally teach, I would actually hand out an orange to everyone, and I'd ask you to draw latitude and longitudinal lines, a prime meridian, and a little heart over San Luis Obispo on the continental US. Okay, so I'd have you draw all of those on the orange peel. Then I'd ask you to peel the orange and lay the heart of San Luis Obispo, where you drew it, flat and in the center right in front of you on the table. Kind of like in this middle image. You would find that you'd have to distort some of the orange peels. You'd have to move it. You'd have to make some other pieces longer or shorter or in a different area to show that heart. And so because the Earth is curved and maps are flat, we need a mathematical model of the Earth's shape before we can assign coordinates and even create maps. And so this is a topic that has its own major at universities. You could do a PhD in the shape of the Earth. So I just wanted to introduce the terminology ellipsoid, which is the shape of the Earth, or a spheroid. We can use those simultaneously. Just know that that's the shape of the Earth, and it is not perfectly symmetrical. Earth is not a perfect symmetrical, circle, right? There's lumps and bumps, and gravity pulls certain areas one way and it rotates on its axis. So the semi-major and semi-minor axes that fit one geographical region do not necessarily fit another one. And we've established that the Earth is curved, but it's actually a little more complicated than that, right? Like I said, people will go and study for years just this one topic. And if the Earth were a perfect sphere, mapping would be a lot more simple. However, the Earth rotates, causing it to bulge slightly around the equator, and flatten a little at the poles. So mountains and valleys and changes in gravity make its surface even more irregular. So because the real Earth is so complex, GIS doesn't use the actual Earth's surface for calculations. Instead, we use a simplified mathematical model called an ellipsoid. And an ellipsoid is close enough to the Earth's shape that it allows us to accurately calculate locations, distances, and areas around the world. And so the shape of the Earth is a spheroid, but we use the ellipsoid as the mathematical model. And the actual Earth is even more irregular than an ellipsoid because of variations in gravity. So scientists model that with something called a geoid. But for most GIS applications, we use an ellipsoid as our mathematical reference surface. Now that we have a mathematical model of the Earth's shape, the ellipsoid, we need a way to describe locations on it. That's where a geographic coordinate system comes into play, otherwise known as a GCS. So from here on out, we'll call that a GCS, but that is one of the two types of coordinate systems. And so key components of a GCS include latitude, longitude, prime meridian, datum, which is the ellipsoid. It's the mathematical model that of the Earth used as a reference surface. An example of that ellipsoid would be WGS 84. So that's a common GCS that we see in ArcPro. And then another key component, and very important, is that it uses angular units for measurement. So latitude and longitude are measured in degrees, minutes, and seconds, not linear feet. And so the graticule of latitude and longitude lines is an angular measurement system, like I just explained in the last slide. All features on the Earth's surface are located using measurements that are relative to the center of the Earth. So in this bottom diagram of Earth, you could see this 3D image and how it's an angular measurement. That kind of helps illustrate that. A prime meridian is the zero value for longitude. While the official prime meridian passes through Greenwich in southeast London, UK, the choice of prime meridian for a given coordinate system is somewhat arbitrary. It is not necessarily to define a zero value for latitude because it is always the equator. And so there are two types of coordinate systems. I already went over one, which is GCS. And then the second type is a projected coordinate system, or PCS. And so you need a GCS in order to make a PCS. I know it's a lot of acronyms. A projected coordinate system is based on a geographic coordinate system. So if you were in class with me and you had that orange, the orange peel still on the orange would be your GCS. When you collect the data, you use a GCS and you plot it on the orange peel. And then as you peel the orange and you flatten it, that becomes the projection. So that's the PCS. So projected coordinate systems are used to convert feature locations from the spherical Earth to a flat map. And PCS turns latitude and longitudes from GCS into a flat 2D coordinate system. A GCS tells us where something is on Earth's surface. Like if you're looking at that whole orange, it shows you where it is. And then as you peel it and lay it flat, that shows you where it is on a map. And degrees are excellent for locating places, but they're not practical for measuring distances, areas, or creating accurate maps. That's where a projected coordinate system, or PCS, comes into play. And so a PCS takes that curved Earth and projects it onto a flat surface. And here's kind of more of an orange peel analogy. So in the top image, you could see as if you peeled an orange and laid it flat, like that's the different distortions you see and what the different distortions of projection would have. This is an image in ArcPro, and we'll see this later in lab, but you can look in the map properties and see the geographic coordinate system and the projected coordinate system if they have it. Not all data have both. Some may just have a geographic coordinate system, which we will see in lab later. So again, a GCS defines where the data is located on the Earth's surface, and a PCS tells us how to draw on a flat surface because it's projected and it has that mathematical equation behind it, which tells us where and how to distort it. A simple way to think about the difference is that a GCS helps us locate places, while a PCS helps us measure them. A GCS uses latitude and longitude in degrees on a curved surface, making it ideal for global datasets and GPS. A PCS transforms those coordinates onto a flat map using a specific projection, allowing us to accurately calculate distances, areas, and directions. In GIS, we often start with data in a geographic coordinate system and then project it into a PCS. So let's take like a real world example. An injured hiker sends you her latitude and longitude from her satellite phone. This is a canyon in Arizona. And so you have her lat and longs. It's 134.577 degrees east and 24.006 degrees south. Where is she located? And the answer is this image on the right, which is showing those lat and longs. And how can the exact same coordinate point to two different locations? And that would be tricky, right? If you tried to locate her and you arrived at two different possible locations, which one do you search? And why is that? Well, the answer is it's the missing piece, the geographic coordinate system. So when we think of latitude and longitude, we usually assume they're enough to identify a location, but they're only part of the story. Think of lat and long like a street address. If I tell you 123 Main Street, you still need to know which city I'm talking about, right? It could be in multiple cities across the US. In GIS, latitude and longitude work the same way. You also need to know which geographic coordinate system those coordinates belong to. So in this example, the coordinates are identical, 134.57 degrees east, 24.006 degrees south. Those both describe A and point B. Point A is based on the Australian geodetic datum 1984, while point B uses WGS 1984, which we often see as a default in ArcPro. So because each coordinate system uses a slightly different mathematical model of the Earth, the same numbers point to different places. So if you're conducting a search and rescue mission, that difference could mean searching on top of the plateau instead of the base of the cliff. That's why one of the first things GIS professionals check is the coordinate system of their data when they collect it. So once your data knows where to draw it, it needs to know how. How can we show this on a flat map? We need to know what projection to use. The Earth's surface and your GCS are round, but your map and your computer screen are flat. So that's a problem. So it's really important to know which projection to use. And there's certain ways to figure that out. You can, like for San Luis Obispo, we use State Plane NAD 1983 Zone 5. And a lot of the times you can Google and look up which state plane are we in, Monterey County or SLO County, or it changes throughout California. And that information will be online. So in ArcPro, you can view the details of any coordinate system in the Map Properties map, and we'll go over this in lab. But basically, the map, when you insert a new map, that map has a map property, and your layers also have their own properties of coordinate systems. And here's a details page. When you look at a coordinate system in the layers properties or the map properties, you're going to see all these different characteristics. And so the first line tells you that it's a projected coordinate system as opposed to a GCS. So you see the difference, projected coordinate system versus geographic coordinate system a little bit below that. You have other characteristics like WKID, which is a unique identifier number for the PCS defined by its authority. You have the measurement. So is it angular units or is it linear units? So that depends on which coordinate system. False easting, false northing, and option are parameters specific to the fuller projection. Other projections have parameters like central meridian, standard parallel, and latitude of origin. You're not going to need to know these for these class. I just wanted to introduce these keywords. You can often modify these parameters to center the PCS on a specific location. And then when a layer has a PCS, a projected coordinate system, it will also contain the geographic coordinate system that the data was collected in. So in summary, your key takeaway is the GCS tells you where something is on Earth, and the PCS tells you how to map it. And there's key characteristics for each, which we're going to go over in lab this week. But you always want to check, what is the data's coordinate system? Is it appropriate for your area and purpose? Do you need to project it to a PCS for analysis, or is it already projected? And document the coordinate system you use in any transformations. Okay, thanks for listening and watching, and let's continue with this week's content.